This video tutorial focuses on the refraction of light and total internal reflection. We are going to analyze problems on this property of light. So just take it easy and watch and learn. Our first conceptual problem. The drawing shows 3 layers of liquids A, B, and C, each with a different index of refraction. Light begins in liquid A, alright, that's liquid A, passes into liquid B, and eventually into liquid C, as the ray of light in the drawing shows. The dashed lines denote the normals to the interfaces between the layers. Question is, which liquid has the smallest index of refraction and why? So the illustration assumes that the angle of incidence of this light ray as compared to the angle of incidence in liquid C or in liquid B, okay, it appears to be the smallest. In other words, we may assume that in this drawing, the angles are all drawn to scale. So in the next slide, we are going to illustrate how we can answer this conceptual question. Okay, the concept that is applied in this question is that whenever a light ray enters from a medium of higher refractive index to a medium of lower refractive index, it is refracted away from the normal line. So, as you can see in the illustration, this is the incident light ray, okay? And the angle formed by the incident light ray with the normal line is what we call the angle of incidence. When it enters, okay, the second medium or liquid B, you will notice that the refracted ray, this is the refracted ray, is refracted such that it bends away from the normal. Okay? So again, when it is about to enter another medium, liquid C, okay, the bending is such that the refracted ray in liquid C is towards the normal. So it means that according to our concept, okay, it looks like that liquid A, okay, liquid A has an index of refraction that is higher than that of liquid B. Okay, the fact that upon entering liquid B coming from liquid A, the refracted ray, okay, is bent away from the normal. So comparing the index or the indices of refraction, okay, between liquid A and liquid B, we can therefore say that that of liquid A is greater than the index of refraction of liquid B. And then comparing the two indexes of refraction between liquid B and liquid C, okay, our conclusion is that the index of refraction of liquid C is higher than that of liquid B, the fact that from liquid B to liquid C, the refracted ray is bent towards the normal. Okay, that is what our illustration suggests. And therefore, okay, combining these two comparisons, we can therefore say that the index of refraction of liquid B is the smallest among the three indexes of refraction. For our second problem, a light ray strikes an air-water surface at an angle of 46 degrees with respect to the normal. The refractive index for water is 1.33. Find the angle of refraction when the direction of the ray is, letter A, from air to water, and B, from water to air. So this problem is a typical problem on Snell's law, and the solution is just a straightforward application of that law, which we call Snell's law of refraction. This is uh, the formula of Snell's law, which reads the sine of the angle theta 1 multiplied by the index of refraction of medium 1 is equal to the sine of the angle theta 2 multiplied by the index of refraction of medium 2. All right? So, our assumption is that, okay, uh, wherever is the light, okay, is coming from, okay, the medium where the light is coming from, that is considered as the first medium. Okay? And the second medium where the light is going into is what we call the second medium. So, light ray starts from medium 1 and then it enters a second medium, medium 2. And the angle theta 1 here is understood to be the angle of incidence. Okay, the angle of incidence that is formed by the incident light ray with respect to the normal line. Likewise, the angle theta 2 is defined as the angle of refraction, which is the angle formed by the refracted ray with respect to the normal line. Since there are two questions, letter A and letter B, we'll answer letter A first. Our formula for finding the angle of refraction, let that be theta 2. Okay, so the sine of that angle theta 2 is just, okay, equal to sine of the angle of incidence multiplied by the index of refraction of medium 1 divided by the index of refraction of medium 2. So substituting the given data in our equation, we will get sine of 46 degrees, right, multiplied by the index of refraction of air is 1.00 divided by the index of refraction of water, which is 1.33. And solving for this, we will get our value for the theta 2. Okay? Before we get this angle, you have to apply your definition of arc sine. Or if you have your scientific calculator, you just use the inverse of the sine of the angle. Okay? I'm sure everybody knows how to uh, manipulate in using your calculator. Okay? Arc sine is just the same as inverse of the angle. So we get the value for theta 2. This is the angle of refraction when the incident ray moves from air to water. Now for letter B, what about if the light ray enters from water to air? So we are going to reverse, okay, the direction of uh, the light ray. The same formula will be applied. Okay, our theta 2 represents the angle of refraction of the light ray when it enters from water to air. This time, water is the first medium and air is the second medium. So, substituting once again the given data, okay, we get the sine of 46 degrees multiplied by the index of refraction for water, which is 1.33, and simply divide them by index of refraction of air. And again, doing your arc sine method, determining the angle theta 2, we will get, with the help of your calculator, we will get the value of theta 2, which is equal to 74 degrees. So, it looks like that when the light ray starts from a medium such as air, whose index is lower, and it enters a second medium whose index of refraction is higher, the angle of refraction, okay, will be less than, okay, to the angle of refraction when the direction uh, of the light ray is, okay, from water to air. Okay, that is what we can conclude about the difference in the angle of refraction for the two cases in this second problem. Our third example is a common observation when you are looking into the bottom of a pool. Okay, you are actually looking at a depth that is not real. Okay, to some people, the depth of a pool might not be or might look as if it is shallow. Okay, but don't be deceived because what you see is just the effect of light being refracted. So we have here an illustration first before we analyze the given problem. All right. So for example, here you are the observer, and you look down into the bottom of your swimming pool. Okay. Let's assume that the bottom of the pool is labeled here as PQ. All right. PQ. So we can imagine that a light ray coming from this object, PQ, okay, will be traveling through the water and strikes the surface. Okay, the light ray is a light ray coming from point Q. When it strikes the surface from water and goes out into the air, all right, water being or having a higher refractive index than air, what happens is that the light ray or the refracted light ray will bend away from the normal. So we can imagine the normal perpendicular line to the water surface. And that exactly the refracted ray that will hit the eye of the observer. Okay? And if this refracted ray, okay, from the vantage point of the observer, if this is extended, all right, if we extend that refracted ray backwards until this point, okay, that is how the observer, okay, will interpret, okay, the image of point Q. It is as if, okay, it is as if point Q is located at this point, whose depth is much lower. S prime represents the apparent depth, okay, while the actual depth of the pool is represented here by S key. So that's exactly the effect of light being refracted as it passes from water to air. So our question is, supposing a non-swimmer looks straight down into the water that is actually 2 meters. Okay, so the actual depth of the pool is 2 meters, which is about 6 feet and 7 inches deep. Question is, how deep does it appear to be? Right, so we are looking for the apparent depth of this pool. And our formula for determining the apparent depth is a derived formula using, again, the concept of um, refraction of light, and it's also related to what we've learned about image formation, okay, by lenses. All right, but we are not going to discuss here how this formula, okay, has been derived. So I'm giving you the actual uh, formula now. It is what we call determining the apparent depth, labeled here as H prime. So H prime, to get the value of H prime, we just multiply the actual depth represented by the letter H multiplied by the ratio of N1 over N2. So N1 refers to the refractive index of air, while N2 is the refractive index of water. Okay, so this is the formula for determining the apparent depth of a pool. There may be instances when what you're going to calculate is the actual depth. Instead of H prime, you will be asked to calculate for actual depth, H. As long as you know the basic formula, okay, you can easily derive the formula depending on what you are going to calculate. So I leave that to you, how you are going to express uh, or what is the formula, working formula for determining the actual depth given the apparent depth. This problem requires us to determine the apparent depth. So this is our formula. And if you're going to substitute, okay, H prime now will be equal to 2, which is the actual depth. That's 2 meters actually. And multiplied it by the ratio of N1 over N2, where N1 is equal to 1 or 1.00 index of refraction of air divided by the index of refraction of water, which is 1.33. Therefore, the apparent depth of the pool will just be equal to 1.5 meters. Right? You will notice that the apparent depth has decreased by as much as 75%. Okay? 1.5 meters is actually 75% only of 2 meters. So maybe next time if you're asked the same question, what you can do is just to multiply the actual depth by 3/4 or 0.75, and you will be able to get the apparent depth. That is the shorter way of finding the apparent depth, knowing the ratio of the index of refraction of air to that of water. All right. So this is the answer to our question. And what is the moral of this story? If you are the swimmer and you happen to be a 6 feet tall a non-swimmer, okay, and uh, you try to look at the depth of the pool. So according to you, it looks shallow. Okay, it looks shallow. What appears to be 2 meters will only appear to be 1.5 meters. So if you are a 6 feet non-swimmer in this situation, and uh, you are tempted to jump into the pool, I'm sure you will be in trouble. This is not the last problem. Light is incident along the normal on face AB of a glass prism of refractive index 1.52 as shown in the figure. Find the largest value the angle alpha can have without any light refracted out of the prism at face AC if, letter A, the prism is immersed in air, and B, if the prism is immersed in water. Let the index of refraction of air equals or equal to 1.00, and for water, the index of refraction is equal to 1.33. So in the diagram, okay, there is an incident ray that is going to enter a glass prism, triangular glass prism, such that the angle of incidence of the ray is 0. It is perpendicularly, uh, it is perpendicular to the face AB, okay, of the prism. So the question is, will this incident ray be refracted? In other words, will it have a change in direction? Will it bend once it enters the glass prism? Okay, so we will find that out in our next slide. Alright, so the question that I asked earlier is, will the incident ray bend as it enters the glass prism? If the angle of incidence is equal to 0, is this light ray going to bend with some angle of refraction, or will it just go straight? Alright, so the answer is there will be no bending. Okay, that is the case when the angle of incidence is equal to 0. Alright, it can be shown using Snell's law that if the angle of incidence is 0, then it follows that the angle of refraction will also be equal to 0. So there will be no bending that will happen at the AB interface. And technically, when a light ray doesn't bend as it enters from one medium to another, we cannot call this refraction, because the word refraction really suggests some kind of bending. There may be a decrease in the speed of the light ray as it enters, okay, from air to glass, because glass has a higher optical density. So the speed of light when it enters a medium such as glass kinda decreases in magnitude. Alright, so we will indicate that uh, incident ray as it enters the glass prism with this arrow or light ray. Alright, so what's going to happen now if at that point, okay, the point along the interface AC or phase AC, is it going to emerge into the air, or will it be reflected internally within the glass? The situation is that the first medium is the glass, whose index of refraction is higher than the index of refraction of air, supposedly the second medium. So this is the case where uh, total internal reflection can occur. Okay? Total internal reflection happens only if the incident ray is coming from a medium with higher index of refraction and going into a second medium with a lower index of refraction. We cannot have the reverse, air to glass or air to water. That that cannot. Total internal reflection cannot happen. Okay, only if the first medium is of a higher index of refraction going into a medium with lower index of refraction. But then again, it also depends on what the angle of incident or incidence of the light ray will be at that point. Okay. To help us out in our analysis, let's draw the normal line or perpendicular line to that interface AC. And we will also choose angle theta. Angle theta here is the maximum angle that we are looking for. It is the angle formed with the normal at phase AC. Okay? And we can call this angle the critical angle theta C. So why is it called critical angle? Okay. It is like this. Supposing we start with uh, the incident ray having an angle of incidence that is too small. Alright? Too small or smaller compared to what we call the critical angle. So what's going to happen to that incident ray when the angle of incidence is very low compared to the angle or critical angle? Okay, the answer is it will just emerge into the next medium, which is the air. In other words, it will be refracted following the law of or following the Snell's law, meaning as it enters the medium with lower index of refraction, the light ray or the refracted ray will be bent away from the normal, right? Such that the angle of refraction will be greater than the angle of incidence. Now, what will happen if the angle of incidence while still inside the glass? Okay, uh, what will happen to the refracted ray if the angle of incidence within the glass is increased? All right. So if this angle of incidence, okay, is increased and as it approaches the angle of critical angle, okay, theta, what will happen to the refracted ray is that it will just uh, be refracted along the boundary of the glass and the air, meaning along the interface AC, as shown by that red arrow, okay, whose angle of refraction will just be equal exactly to 90 degrees. Okay, that is the meaning of the critical angle. It is the angle, okay, formed by the incident ray with the normal line okay, such that the refracted ray will just be exactly along the boundary or interface AC, okay, where the angle of refraction is exactly 90 degrees. Now, what's going to happen if the angle of incidence is further increased beyond the critical angle? Okay, if that happens, if the angle of incidence is above the critical angle, what will happen to the ray now? It's not going to emerge anymore into the next or second medium. It will just be reflected internally Internally meaning within the first medium, or in this case, the glass. All right? So this is the phenomenon known as total internal reflection, where the law of reflection of light applies. So whatever is the angle of incidence uh, will also be the angle of reflection. Okay, say for example, if the critical angle is 45 degrees, okay, that's just an example. If the critical angle for the glass is 45 degrees, and the angle of incidence, say for example, is 50 degrees, so 50 is higher than the critical angle, okay, what happens is that there will be total internal reflection, okay. The incident ray will just be reflected internally, forming an angle of reflection also equal to 50 degrees. So there will be no refraction that will happen. Okay? In other words, this so-called critical angle is so important because it determines whether or not uh, an incident ray is going to leave, okay, the first medium and emerges into the next medium, or whether there will be total internal reflection that will happen. But what is the formula for finding the critical angle? All right, the formula is just equal to the arc sine of the ratio of n2 over n1. All right, where n2, of course, is the index of refraction of the second medium, all right, such as air, while n1 is the index of refraction of the first medium, such as glass. All right, take note. In the problem, we are asked to find the value of angle alpha. All right? How is angle alpha related to angle theta? If you notice, we can see here uh, the relationship between two similar triangles. The bigger triangle, all right, the bigger triangle ABC, that's the bigger triangle, has the angle alpha, okay, formed according to the drawing. And that angle here, all right, which is the complementary angle of the critical angle theta, is just equal to alpha, isn't it? Okay, because this is a 90-degree angle, all right. That angle is 90 degrees. So that means whatever is the angle theta, also known as the critical angle, therefore its complementary angle, meaning 90 minus theta, will also be equal to alpha. All right. There are two cases given in the problem. The first one is to find the angle alpha, or the angle theta first, then angle alpha, if the surrounding medium is air. Okay, that's in letter A. And then in letter B, what if the surrounding medium is water? So let's begin with letter A. Letter A assumes that the surrounding medium is air. So in our formula for finding the critical angle theta C, okay, we just use that formula. All right. The arc sine or inverse sine value of 1 over 1.52, because the index of refraction of N2, that's for air, is 1. And for the glass, it's 1.52. And using your calculator, we can find the value of the critical angle theta C, which is equal to 41 degrees, exactly 41 degrees. And since what we are looking for is angle alpha, we just get the difference. 90 minus 41 will give us, of course, 49 degrees. Okay, so this is the angle we're looking for. The greatest angle, uh, alpha, such that there will be no refraction that's going to occur. And in letter B, we just replace the index of refraction, um, N2. Instead of air, we use now the index of refraction for water. which is 1.33, and divide that by the index of refraction of the glass still, and getting the arc sign, okay, for that ratio, we will be able to get the critical angle for the case where the surrounding medium is water, and the value is exactly 61 degrees. Therefore, the unknown value for the alpha is 90 minus 61, which gives us exactly 29 degrees, right? So when you compare the two angles, you will notice that if the angle, if the surrounding medium, has a lower index of refraction, then the critical angle for that material, in this case, the critical angle for the glass is lower as compared to uh, the critical angle of the same material, the glass, surrounded by a medium such as water, whose index is much larger. Okay, 61 degrees is the critical angle of the glass when surrounded, okay, by water, while 41 degrees is the critical angle of the same glass when surrounded by air. So, in this problem, we were able to answer the question simply by applying the principle of Snell's law, as well as incorporating the concept of total internal reflection, which is associated to uh, critical angle. All right, so that will be all for today, and hope to see you in the next video tutorial.